type of an ODE is this? Well, to answer that, we first need to understand what an ODE is, an ordinary differential equation, and then understand what the different types are before we can answer that question. So we're going to start there. The first thing that I want you guys to understand is what a dependent variable is. So a dependent variable is basically the y value that you have. So it's a value that depends on other values. Then we have what we call an independent variable. So it's a variable that doesn't depend on anything else. So it's what affects the outcome. This can be time, this can be position, it can be anything really, but we like to just call it x. So an dependent variable is y, which is related to x. You can see an equation that says y is equal to x squared. So y depends on the value of x. You can see equations such as y is equal to 2x. So y depends on the value of x. So these are equations that you might expect to find. You can also have a quantity or something that we call gradient. So gradient is basically dy over dx, the rate of change of y with respect to x, the gradient of this specific graph. So if you look at this expression, y is equal to x squared, the gradient is going to be 2x. Okay, so dy dx is basically the gradient of that specific graph. And we can also have the second derivative, which is basically the gradient of the gradient, right? How the gradient is changing with respect to x. So in this case, it's going to be the derivative of 2x, which is just 2. So this is what we mean by saying we have a dependent variable y and an independent variable that we can compute to find the gradient. But we have something that's quite important that's called an ordinary differential equation that we want to basically talk about. So we're going to define what it is. So I'm going to call it ODE for short so that we don't waste a lot of time. So basically, an ODE is an equation that relates a function or the y value and its derivatives. So it's y in this derivative with respect to one independent variable. So it's ordinary, right? We only have one independent variable. So what do I mean by this? Look at this equation. Okay, it's a little bit complicated, but you're going to see that these are basically derivatives of y. So this is a derivative of y, second derivative. This is a derivative of y, so I'm going to call it d of y. This is y itself, and this is an independent variable. So you see that x is basically the independent variable. Okay, so this is basically what we call an ordinary differential equation, an equation that links the derivatives of y to the values of y itself as well as the independent variable. So if you look at this, you can basically say that this is an ordinary differential equation because you have the gradient or the derivative of y being linked to an independent variable x. This is also an example of an ordinary differential equation. You have the gradient or the second derivative being linked to a constant value. Now, there are important things that you must be able to define. The first one being order. So what does order refer to, right? Order basically refers to the highest derivative in the equation. Okay, so if you look at this equation and you ask yourself, what is the highest derivative? In this case, it's 2d squared y over dx squared. So for that equation, it's going to be 2, right? If I give an equation that says d cubed y over dx cubed is equals to 5, the order is going to be what? It's going to be 3, right? If I give you d to the power of 4y over dx to the power of 4 is equals to 5x, the order is going to be 4. Okay, another important thing that you must know is basically what a solution is. So if you see an equation that relates derivatives to independent variables, which are values of x, that's what we call an ODE. And an ODE can have order, which basically just refers to the highest derivative that you can find. That's the order of your differential equation. It can be second order, first order differential equations. And our whole goal is to find a solution. So what is a solution to an ODE? It's basically a family of functions that satisfy the equation or the ODE. Okay, so if you look at the example that I gave you here, for this one, you can basically derive an expression that says y is equal to a e to the power of 3x. So don't worry about it being a bit complicated. It's going to be fine. Or something like this. Basically, this is what we call a solution. What family will exist? So you can have different values of a. So you can see I have this constant a and this value of b over here. So we call these families of or functions basically that can satisfy this equation, right? An easy example of a solution is if I were to give you an ODE, an example, if I were to give you a simple ODE saying dy over dx is equals to 2x, for example, you can easily see that, okay, if I were to integrate this, y is equal to 2x squared divided by 2 plus c. Y is equals to x squared plus c. So this is what we call a solution, right? It's a family because you can have different values of c. So that's why we call it a family. Okay, so remember I asked you when I started, what type of an ODE is this? So you can tell me that this is an ODE because now you're seeing that, oh, this is a derivative of y, or this one independent variable, so it's an ODE. But I asked you what type it is. So we need to be able to classify ODEs to talk about the types of ODEs. So that's what we're going to talk about now. So classifications of ODEs. Okay, so the first classification that we're going to talk about, so classification number 1 is linear versus non-linear ODEs. Okay, so an ODE can be said to be linear or non-linear, and we need to understand what that means. So first up, it's linear. An ODE is linear if the following is satisfied. Okay, so I'm going to explain what this means, right? I don't expect you to memorize this. I'm going to explain what this is simply. So how do you tell if a function is linear? Okay, if an ODE is linear, basically, I'm going to need you to follow these 2 rules. So this is basically the 2 rules that you're going to follow, and I'll explain what all of this is. Okay, so the first rule that you need to follow is that in front of y and its derivatives, you must, I repeat, you must only have pure functions of x. Okay, you must only have pure functions of x. So what I mean by this is that if you have dy over dx, behind it there must only be pure functions of x, e to the power of x or cos x dy over dx. You know, you can't have situations where you have y squared, or situations where you have y dy dx, right? Having another function behind the derivative. So in front of y, like behind it, so I mean in front, like behind it, like this, of y and its derivatives, you must only have pure functions of x. So that's the first rule that you need for a linear function. So that's why you see that I have this. All of these are just pure functions of x behind y and its derivatives. So that's why I have a naught 0x is just a function of x, basically. That's another function of x. So behind the derivatives and values of y, there must only be pure functions of x. The second rule that you must follow to be a linear ODE, if you're not a linear, you're a non-linear ODE, is that y and all its derivatives are to the first power. Okay, so y and all its derivatives should be to the first power. And this is very important, very easy to see. So for example, if you have dy over dx squared, right? So remember, this is not d squared y over dx squared. These are completely different things. This is second order. This is first order squared. Okay, so if this is present in your equation, you can now tell that, oh, my equation is non-linear because this is present, right? But if this is present, your equation is linear because the derivatives in this case is the second derivative. It's to the power of 1, so it's to the first power, and that's a linear function. We're going to look at a couple of examples. Okay, so I'm going to ask you whether it's linear or non-linear. We're going to play a little game. Is it linear or is it non-linear? The first example, d squared y over dx squared plus e to the power of x dy over dx plus y is equals to sine x. So this is g of x, like sine x in this case is g of x, which I said here is g of x, just a function of x. It shouldn't be a function of y. For example, if it's like y squared, that's not going to work. Or it can be 6 or any number. It doesn't really matter. But if you look at this, what did I say are the rules to determine whether it's linear or non-linear? Behind every value of y and its derivatives, there must be pure functions of x. So you first look at this. Is there any weird thing behind it? No, there's one. So that's good. If you look behind this, there's e to the power of x, which is a function of x. So that's good. Behind y, there is a 1. So that's good. That's a function of x. And this is sine of x, which is good. This is just a function of x, basically, or g of x. So this is good. So I can safely say that this is linear. Example number 2, if I give you d cubed y over dx cubed plus 3y d squared y over dx squared plus y squared is equals to e to the power of x. We play the same game. You look at the coefficient of this. Is it the number in front of this is 1? So 1 is a pure function of x because 1 is basically x to the power of 0. So that's good. We come here, we look behind the coefficient, or we look behind d squared y over dx squared or its coefficient. We realize that, oh, it's actually 3y. 3y is not a function of x. So this is basically non-linear. If you look at y squared, oh, this is actually y times y. So behind y, there's another y. So this is non-linear at all. I hope you're getting the gist of this. I'll do one last example to solidify this concept. The square root of dy over dx plus 3y is equals to sine x cos y. Okay, something like this. So we can basically see that, oh, something is happening here, right? If you look at this, this is basically dy over dx to the power of 1/2. So, oh, this is not, so the power of dy dx is actually not 1. So this is non-linear because of that fact. We'll look at 3y, that's good. No, nothing wrong there. The coefficient of cos y is actually sine x, so that's good. So this is basically non-linear. So that's basically how you determine whether or not a function is linear or non-linear. So another way you can tell or what type a function is in ODE is whether it's linear or it's non-linear. Another class that we're going to talk about, or another type of ODE, or how you can describe ODEs, is whether they are homogeneous or non-homogeneous. So we're going to start off with the first one being homogeneous. So we start off with homogeneous. And you can basically tell that the opposite of homogeneous is going to be non-homogeneous. So what does homogeneous mean? So it basically means that all of the terms involve the dependent variable, so just the dependent variable and its derivatives, such that g of x is equal to 0. Okay, so if we're gonna look at our function over here that we defined over here, if g of x, which is basically this fella over here, is equal to 0, then we are homogeneous. As simple as that. So that's what we call a homogeneous ODE. And I'm going to give you a couple of examples to distinguish between homogeneous and non-homogeneous ODEs. And I'm going to ask you guys to just think first, then speak out loud. You can pause if you want to give it a go. You can see that the coefficient of this is 1, this is 1, this is y, so this is linear. That's good. And then if you check for the value of g of x, in this case, the term that's independent of y is what we call g of x. So g of x in this case is equals to 0, so it's also homogeneous. So that's good. We look at example number 2. If you look at this, this is basically squared. So the power of the derivative is not actually 1. So this means this is non-linear. And if you see also here, the coefficient of dy dx is actually 3y, so it's still non-linear. But if you look at this, the term independent of y is actually equal to 5, which is not equal to 0. So it is non-homogeneous. Okay. Another way you can describe an ODE. So now you can tell me, if I give you an ODE, you can tell me that this is a nonlinear, non-homogeneous ODE, or this is a nonlinear, homogeneous ODE. Another way you can describe an ODE, or what type it is basically linear ODE with constant coefficients. Okay, so the coefficients of y and its derivatives are basically independent of x. That's what this means. So the coefficients independent of x, right? In this example of this is basically, so mathematically, if you want to be complicated, mathematically what this looks like is just, you know, a complicated, but this is very fine. Just means the coefficient of all the powers is basically like constants, not necessarily functions of x. So it isn't an as a function of x. Okay, just important for you to know. 6. So first you can see that y and all its derivatives don't have any function of y as its coefficients, and they're not powered to anything, not 1. So this is basically linear, and it's also non-homogeneous. Non-homogeneous because g of x is equal to x to the power of 6. The term independent of y is x to the power of 6, which is not equal to 0. So this is non-homogeneous, and it has constant coefficients. So if you're asked to describe this, you can basically say this is a linear, non-homogeneous ODE with constant coefficients. So we started off introducing this term over here, dy over dx is equals to y over 2x plus y cubed. So we can multiply both sides by, so this is our question. I'm going to put my solution over here. So we can basically multiply both sides by 2x plus y cubed. So dy over dx multiplied by 2x plus y cubed is equals to y. So basically, we have, it depends. You can factor it out. You can leave it like this if you want. You can factor it out and just have 2x. Or you can put it to the other side. So minus y is equal to 0. Then you start looking at the coefficients of the derivatives. So dy dx has a coefficient of 2x, which is a function of x. So that's good. But here, oops, we have y cubed. So by default, this is non-linear. Okay. And then is it homogeneous? So you can see that g of x is equal to 0. The term that's independent of x is actually 0. So this is homogeneous, which is, well, I can't say it's good, but it's just, you know, something that we know, homogeneous. So that's good. And then does it have constant coefficients? So it doesn't really have any constant coefficients because we have 2x. So if I was asked what type of an ODE is this, I'm going to say this is a non-linear homogeneous ODE. And I'll be done.